Kia ora koutou, no mai haere mai. Welcome to lesson 3 for introductory physics. This lesson is on vectors, but also on frames of reference. So vectors is going to be obviously mathematics based. We're talking about what vectors are. I don't expect you to have met them before, but given your expected trigonometry and geometry sort of knowledge, vectors shouldn't pose much of a problem. Then we're going to talk about frames of reference, which is a physics sort of way of thinking about a specific scenario. So we'll have a look at all of that. As usual, I will jump over and we'll look at the lecture slides and I'll narrate through. So lesson 3, vectors and frames of reference. First of all, as I said, vectors and vector addition is what we're going to look at. So defining vectors, most numbers are just scalars. That means just a number and there's no direction involved. If I ask you how many apples you have and you say you've got 5, that's a scalar. There's just a quantity, just a magnitude to that number. If I ask you how long something is, that length is just a scalar. There's no direction involved in its length because you can move that object. But vectors are magnitude and direction. So it's anything that has a direction involved with it. As an example there, if I say Bob is 5 meters away, I've described a scalar because I've just given you a magnitude. I don't care about the direction. All I care about is that distance between me and Bob. But if I say that Bob is 5 meters due north, by introducing that direction, I've turned it into a vector. So a vector is just a magnitude with a direction as opposed to just a magnitude. We commonly draw these kind of like a graph. So if you're all familiar with graphs, you have an x-axis and a y-axis. The x-axis has been cut off a bit here just to make it fit on the slide, but the x-axis and the y-axis, and then you draw your vector onto it because now the direction is involved. That just means you're pointing in a different way. You might point directly along the x-axis or directly up the y-axis, or you might point somewhere in between. You should always start at the origin, at that 0 point where the two axes cross, and then you draw your vector on. You might write it as I have here and say 2x plus 3y. So you're literally describing how to get from the origin to the end of that vector. You start at the origin, you have to go along 2 on the x-axis and then up 3 on the y-axis, and the point where you end up, that is the end of your vector. And so the vector is the arrow that points from your origin to that position at 2x, 3y. Obviously, you don't necessarily follow that path. If someone was traveling from the origin, from O to A, that's the end of this vector is labeled A. If you're traveling from the origin to A, you'd probably just do it, well, you may do it in a straight line, you may not. It's something we'll talk about when we talk about basic motion. But the 2x and 3y is just a descriptor for how to find that end point based on this coordinate system. The two different components of that, the x and the y, are called components, and they, as I said, they just tell you in that frame, that x and y frame that you've drawn, how to find that endpoint. However, sometimes we don't know the x and the y components. In that case, we might describe it like this. We might say, well, it's 3.6 long. I haven't got units on this, so I'm leaving units off. So 3.6, whatever the units are, long. And the angle is 56 degrees relative to the x-axis, or above horizontal. So you may, or you will often see vectors described like this, as a length, a magnitude, and a direction given by an angle. Sometimes we use compass directions. If you're not familiar with compass directions, I'm sure you all are, but I'll just draw them very quickly over here. Compass directions are just this idea of north, east, south, west. And so when we talk about compass directions, if we're talking directly along one of them, so that would be directly north, that would be directly south, and so on. But we also talk about things like northeast. So that would be northeast. And if you say northeast, that means exactly 45 degrees in that direction. Southwest would be obviously the opposite, exactly 45 degrees that way. And so on. We won't get any more complicated than that in this course. It does get more complicated. If you're really interested, you can look it up, but that's all you need to know for this course is northeast, south, and west, and then northeast means halfway between north and east. So that's all you need to know for a vector is its length, which is its magnitude, and its direction. So either a compass direction or an angle relative to some fixed direction, like 56 degrees above horizontal, Or you can give the two components, the x and the y, where x and y are perpendicular to each other. And then from that, it's enough for anyone to figure out the vector itself. We will do a lot of vector work. As soon as you get into 2 or 3 dimensions, which is something we'll talk about in the frames of reference section, as soon as you get above 1 dimension, we need vectors. They are absolutely required. So please do take the time to fully understand the vector mathematics now. As I said, this first week is sort of preparing you for the actual physics. If you're not confident on vectors, then as soon as we start going into 2 and 3 dimensional problems, everything will fall apart. You need to understand these vectors. When you want to add 2 vectors, again, something we will do a lot. When you want to add 2 vectors, then all you need to do is add their separate components. You take their x components and their y components and you add them together. So doing that mathematically is very straightforward. If you have the vector written as components already, so in this case, vector b is written as 3x plus 2y, and vector c is written as 5x minus 1y, that means that we can just already see the x and y components and we can just add them together, real simple. So when you have it as components, just add the 2 separate components. So that means if d is b plus c, then the x component of d is just the x components of b and c added together. So 3x from b and 5x from c is equal to 8x for d, and that's the x component of d. Same thing for the y components, 2y from b minus 1y from c, add those together, we're left with 1y, which gives us the y component of d, and that's all we have to do. That is vector addition. Sometimes you want to do it graphically, not mathematically, and it's a very good recommendation to sketch it. Even if you don't do it perfectly to scale exactly right, doing it graphically as just even a rough sketch can be a useful check to make sure you've done that mathematical addition correctly as well. So here's what it looks like graphically. We've got vector b is drawn in blue. You can see it's 3x plus 2y. So across 3 on the x-axis, up 2 on the y-axis. Again, we always start at 0 for when we initially draw our vectors. Just start at 0, go across 3, up 2. For c, we go across 5 on the x-axis and then down 1 on the y-axis. And that's that reddish sort of color vector there. To add vectors graphically, all you do is you draw the second one, instead of starting at the origin, you start at the end point of the first vector. So you can see I've done a pale reddish color vector starting at the end point of b, and that is the translated c vector. So translated just means I've moved it in space, that's all it means. So I've moved c vector, so it's still 5 across and 1 down, but it's now starting from the end of that blue vector b, and goes down to here, and you can see that the end point is at 8 across and 1 up. The resultant vector then starts at the origin and just goes directly to that end point of the second vector. So that's all you have to do to add vectors graphically. Again, a good skill to have, a necessary skill to have, I should say. Do practice that, do practice mathematical and graphical addition. On the problem sheet, there are a few questions where I get you to do both, and then obviously check your answers with each other is the whole point of doing it both ways. So do get comfortable with vector addition. Vector subtraction is common, but not as common as addition, but vector subtraction is actually really simple. All it is take a vector. If you're going to subtract a vector, you take it and you flip it. So you make the x and the y the negative of what they were, and then you just add it. So if this vector here, we don't have a scale, but we could say it was 3 across and 2 up, then it would become 3, negative 3, so 3 backwards, and then 2 down. So it becomes just the opposite. Plus 3 plus 2 becomes minus 3 minus 2, and then you can just add it. So subtraction is just flip the vector and then add it. However, if you're dealing with vectors that aren't whole numbers, so those whole number ones are easy. I'll go back a couple of slides. When we look at this one, that's easy because we know our vectors are whole numbers, 3 across, 2 up, 5 across, 1 down, and so it's clear that we've ended at 8 across, 1 up. But as soon as you get into vector addition or any kind of vector mathematics where the vectors are not whole numbers, then it can get a bit messy graphically. It's still a great idea to sketch them and get a rough idea of what you expect out, but it's not such a good idea to then use that to actually count or measure off that final vector. So in that case, what you might want to do is do vector decomposition. So normally, if we've already got the components, vector mathematics is easy. We just add those components to each other. if you don't have the components, if you've just been given a magnitude and a direction, then you might need to figure out those components to do the vector maths. And that's called decomposition, decomposing the component, right, turning it into its components. So decomposing a vector is just taking that vector as its length and an angle and turning it into an X and a Y, or whatever coordinate system you're using. You might be using a north and a south and an east and a west, or you might be using the X and Y or any other coordinate system. So that's all decomposing means, and to do that we need to understand Pythagoras' theorem and trigonometry, which is why those were both in the pre-maths quiz. So do go back, make sure you're happy with those. If you are struggling, then look them up, refresh yourself on those. Again, it's worth taking the time now to make sure you are confident in both the trigonometry stuff, the math stuff, and this vector stuff, which may be new, but it is essentially just the applied trigonometry. So do get comfortable with those. So I haven't given an example. I'll actually just draw one quickly on my sheet of paper, but as you'll see in the problem sheets, there's plenty of practice for you to do this. There's a couple of exercises as well for you to look at some vector addition and stuff after this in the additional resources. But anyway, all vector addition is just decomposing. So if we've been told, we might be told, okay, here's our horizontal. This vector is, say, 30 degrees up, and it's 5 meters long. Then we want to find out the X and the Y components. So we get to choose our X and Y, but if we've been told there's a horizontal, then usually that means you should use that as your X. That means Y will be perpendicular. And so now what we're looking for is the X component, and the Y component. And you can hopefully at this point see exactly what this is going to require. It's going to require figuring out the side lengths of this right-angled triangle. So this is right angles because X and Y are perpendicular. That's the whole point of a coordinate system. X and Y are perpendicular. And so you've got your adjacent side is X, your opposite side is Y. Here's the angle, and you've been given the length of the hypotenuse is 5 meters. So hopefully you're all familiar. As I said, the maths requires you to know some trigonometry. And so in the trigonometry, since we know sine theta is equal to opposite over hypotenuse, and cosine theta is equal to adjacent over hypotenuse. And so we can see here we've got adjacent is our X. So that's X value, that's the length 5 meters, and that's cosine of 30. And here we've got the Y component as our opposite, sine of 30, and the hypotenuse still 5 meters. So rearranging those equations and solving for X and Y is something you do need to be able to do. So that's the introduction to vectors. That's all I'm going to give you on it for now. As I said, do the problem sheet. There are a few questions to work through there. Make sure you're happy with all of that. But now we're going to talk about something you may not have met before if you haven't studied physics, and that's the idea of systems and frames of reference. So a definition to start with is, now I want to be clear, this is my own personal definition. This one is, the next one isn't, but this one is my own personal definition because there was sort of a word missing. So when I talk about a scenario, what I mean is the entire description of the whole world that the problem, that the question is taking place in. So if someone's describing a question, then we call the scenario everything that's relevant to the question. So even just talking about dropping a ball, the ball's part of the scenario, but so is the earth because it's gravitational attraction with the earth that counts and so on. The person dropping it might be part of the scenario depending on what part of the motion you're looking at and all that. So scenario is everything that's actually relevant to the problem in any way. However, the actual physics term that you do need to learn is the one called system. So the system is the specific object or objects that we are actually considering, the ones that we're talking about, their motion or the forces on them. We'll talk about forces in a couple of weeks. So when we're talking about the forces on a specific object, that object is the system. So the system is only going to be part of our scenario, usually. Sometimes we come up with hypothetical scenarios where the system is the whole scenario. But usually a scenario is everything in the system is just one part of it. So as I was talking about dropping a ball, the person dropping the ball, the air that the ball falls through, the earth itself, it's all part of the scenario. The system itself is just going to be the ball because we are concerned with how the ball is moving. So the system is the thing you actually want to understand what it does. Scenario is everything that affects how that system behaves. So again, another example just to hopefully try and drive this home. The system here would be just the ball. We want to know what the ball's going to do. It's confined by the ramp. The earth is the thing that's attracting it. There is air resistance in the way of the ball. So there's all these other things that are part of the scenario. We have to be aware of them because they are relevant to this problem. But the system itself is only the thing we're concerned with knowing how it moves. And in this case, that system is just the ball. We just want to know how the ball travels down this ramp. The next thing that's related to this idea of a system is a frame of reference. So the idea of a frame of reference is just a way that we can turn the motion of any object into numbers, into values that we can record. Because it's no use for us to just say, well, the ball is moving along this ramp. We need to know how far, how fast, and exactly where on the ramp it is and how long it took to get there and all of that. So we need to know exact coordinates of the ball at any point in time. And that means we need a coordinate system. And that's essentially what a frame of reference is. A lot of the time, the frame of reference that we use is just going to be a horizontal axis parallel to the Earth's surface at that point. Of course, the Earth is a circle, it's a sphere, so the surface is curved, but the local area, if you're just looking at a small area of Earth, it's pretty much flat. We can treat it as flat. So x-axis would be a flat line parallel to the Earth's surface, and the y-axis would be a perpendicular line pointing straight up perpendicular to the Earth's surface. So that's sort of a common two-dimensional frame of reference, but you may choose instead to do it relative to a room that you're in or a building. There's other things. We will see plenty of examples where we don't want to use that as a frame of reference because the frame of reference can impact our choice of our calculations and so on. So the choice is very important. As an example, if I want to record my movement within a room, then I would probably just choose one wall as my x-axis, and if it's a square room or rectangular, so the walls are at right angles, I would choose the other wall as y-axis. So I've drawn an example there. We've got x position along one wall, y position along the other. If I give you my x and y values, you know exactly where I am in that room. That's all you need to know, and you know exactly where I am. But sometimes there's motion which, as I said, using a horizontal or parallel to Earth's surface x-axis isn't actually the best idea. For example, let's look at this box on a ramp. So we've got a blue box sitting on an orange ramp. We know from experience that either the box will stay where it is or it will start sliding down the ramp. Those are essentially the two options. If no one's pushing it, if no one's pulling on it, no one's holding it in any way, we've just got a stationary ramp and a box sitting on it. The box will either stay where it is, right? If there's enough friction, if it grips enough to the ramp, it'll stay where it is, or it'll slide down it. So that's all it can actually do, just from our experience. So we want to think about a frame of reference that makes sense in this case. We could use x and y as the horizontal and vertical. And if we do that, then the box starts to move. As it moves, its x-axis its x value would increase and its y value would decrease. So that's perfectly acceptable, but it does make the math more complicated than it needs to be, because we know that it's only ever moving along the surface of the ramp. There's no reason that box would ever come off the ramp. It would just slide down the ramp or possibly stay exactly where it is. So if we instead choose our box to choose the path of our box to be our x-axis, then that means that the position of our box, if we represent that as a value, as in how far down the ramp it's traveled, that's the only value we need. It's actually a one-dimensional problem. We only need the x dimension. We don't need the y dimension because the box is not going to move in that dimension. We would need the y if we were going to talk about our forces, because there are forces in that direction even though the box doesn't move in it. But for now, we're just talking about the motion of the box. The motion of the box would just be straight down the ramp. And since it's all in one straight line, that's a one-dimensional problem, and we should then define our x to be in that direction, and that's going to make all the math much simpler. So we don't we don't have any set rules for choosing a frame of reference. You can essentially choose whatever frame of reference makes sense to you, but you should be aware that different frames of reference for the same problem can involve different amounts of work. You can certainly solve this box problem by using X horizontal and Y vertical, but it will be more complicated and it will make the maths more difficult than if you do it this way with the X parallel to the surface, because now you know that the box is only ever going to change X coordinate. The Y coordinate will not change. Sometimes though, you might want to do something completely different and have, for example, an angle that you're measuring. Right? So if you've got a pendulum, you might measure it as an angle from its center point, what the angle is away from that center, instead of measuring X's and Y's and things. Again, there's lots of options. We're going to keep things fairly simple in this course, and most of the time we'll just stick with our X and Y's, but we will put the X in different positions. It won't always be a horizontal flat X. There is also moving frames of reference. So the classic example is someone on a train drops a ball. If you are on the train and you're sitting next to this boy and he drops the ball and you're on the train as well, you will see the ball just fall straight down. It will look exactly the same as any ball falling down anywhere would. If you drop it, it falls straight down. That's what it would look like to you on the train. But if you were outside the train, imagine the train had one big glass wall for some reason, and you could see in, and you could see this boy drop his ball and it falls straight down for him. For you, it wouldn't look like it's falling straight down, because as it's falling, the whole train, including the boy and the ball and everything inside it, is moving along at some velocity determined by the train, how fast the train is moving. So that means that the ball, when you're outside the train, would not look like it's fallen straight down. It would look like it's fallen in essentially a parabola. We'll talk about projectile motion in a bit. You'll become very familiar with parabolas. But you can hopefully appreciate that it wouldn't look the same. And they are both perfectly valid frames of reference. They are moving relative to each other, but they're still valid. Again, it changes the maths. If we do it on the train, very easy, because the ball is just falling straight down. That's only moving in one dimension. If you look outside the train and choose that, where the earth is your frame of reference, and now the train is moving, and the ball is moving horizontally as it moves vertically, now you've got to consider motion in 2 dimensions, and it becomes more complicated. Right? Again, both are perfectly valid, just changes the maths and the approach that we have to take. Another part of a frame of reference is the origin. The origin is pretty simple. It's just the 0 point for our measurements. So on a standard axis, you've got your X and you've got your Y. The origin is that point where they're both 0, where the axes cross. That's all an origin means. Again, you're free to choose it. Choose a value that makes sense in your problem. So if I go back a few slides for a moment, in this case of this box, it would make sense to put the origin as where the box starts. So you might put the origin right there where the box starts. The other alternative, you could even put the box, the origin is where the box ends up, at the bottom of the ramp. And so you're measuring how far up the ramp the box is versus how far down it is from where it started. Both perfectly valid. And in fact, you might want to use both in slightly different scenarios depending on the exact question that's being asked. So that's all the origin is choosing your 0 point. If I go back again, I'll go back all the way to my room example. The origin, you can see I've already marked that on. I've said the origin is this top left corner. So I move across in the X direction and I move down in the Y direction. So this is an important concept, this idea of frames of reference. And for that reason, I'm going to start a thread on the course content discussion forum, asking you to talk about frames of reference. It's not compulsory, but I do encourage you all to go and have a go to answer in that forum. So there's 3 examples given here, A, B, and C. A is a sprinter on a straight track, B is a pendulum swinging back and forth, and the C is the Earth rotating around the sun. So the question is, what's a good frame of reference and point of origin for studying the motion of each of the following? So what is a good frame of reference and what is a good point of origin? So do head over to the forum and answer one of those. If those have already been answered, then please answer one of the other questions. In terms of other questions, when you answer one of these, please also throw in a new scenario. Just make one up, any scenario, anything that you might want to study, right? Whether it's a roller coaster or a swing or a car on a racetrack, anything. Please don't use one of the assignment questions. I believe there is an assignment question talking about frame of reference. Actually, I think that's within a problem, so that's probably not too much of an issue. There are also a few examples on the problem sheet. So if you're struggling to come up with some, go and read the problem sheet questions as well. That'll also help you answer the questions. But do please get engaged in that discussion. And now, as I've already hinted, we've got the idea of dimensions. So one-dimensional motion is movement restricted to a single straight line. And this is, like I was talking about with that box, if you can represent the motion as a single coordinate, as a single distance measurement, and there's no ambiguity about where the object is, that is one-dimensional motion. If you have something that can move in 2 dimensions, then that means you need 2 coordinates. You need an X and a Y. So just to go back for a moment, our box on a ramp is one-dimensional because we know it will only ever be somewhere along this ramp. So the position along that ramp tells us exactly where it is, one-dimensional motion. But the person walking in the room is 2-dimensional because you need 2 coordinates to tell me definitely where that person is. So one-dimensional motion, when we have one-dimensional motion, we can just represent our position as positive and negative. Even a vector, because a vector has a magnitude and a direction, all you need to tell me the direction when you're in a one-dimensional system is a positive or a negative. If you tell me positive 10, I know that that's 10 to the right in the case of this example here where I've drawn left negative and right positive. If you tell me -5, I know that that's 5 to the left. And so all you actually need to give me a vector in a one-dimensional system is a positive or a negative. And that's all it needs for the direction. If you don't give me a direction, if you just say 5, then that could be 5 to the left or to the right. So the plus or the minus tells me definitively, am I going to the left or the right? So that's all you need for one-dimensional motion. For 2 and 3 dimensions, though, you now need 2 bits of information. You need an X direction and a Y direction, or you need an angle relative to the X-axis or something like that. So you need a full vector with the full directional information. In 3 dimensions, it gets even more complicated because you now need 3 coordinates, an X and a Y and a Z, or you need a magnitude and 2 angles, an angle around along the surface of the, say we're on the Earth, the X along the surface, how far around, and then how far up off the ground. So you need 2 angles and a magnitude if you're doing a 3-dimensional vector. We won't go into 3-dimensional much. I do want you to be aware of it, but generally we're going to deal with 1- and 2-dimensional problems. So this is a very important point, and I will try to reiterate it as we're dealing with some of the force problems. But one-dimensional systems, a one-dimensional system, the positive or the negative is your direction for the vector. As soon as you move into 2 or 3 dimensions, that's no longer enough. The positive or the negative don't really mean anything anymore in 2 dimensions. You now need a direction along with your magnitude. Right? So this is something that isn't often actually discussed in physics. Teachers just sort of assume students will figure it out as they go. Obviously, that's not useful for anyone. So I will try and point this out a bit more. What I'm just going to do quickly is draw a couple of examples. Sorry, I've just got to grab a new sheet of paper. I will just draw a couple of examples just to hopefully reinforce this. So we've got, if we've got one-dimensional motion, then all we've got is this. Here's our origin, here's our X-axis, and we've just got the one axis, and we've got this. And if I tell you that something is moved 5, I won't go 5, I'll go 3 meters. So this is in meters. If I tell you it's moved 3 meters, then it could have gone this way, or it could have gone this way. Right? And so we don't know which of these it is. But if I tell you that it's moved plus 3 meters, the plus is now telling you it's moved in that direction. Right? So that would be plus 3 meters, and that would be minus 3 meters. The plus or the minus is all you need to know that direction. Whereas if you've got a 2-dimensional system, Y and X, and I tell you that it's moved 3 meters, right? Well, what does that mean, right? We have no idea what that means. It could have moved 3 this way, or it could have moved 3 this way, but it could have moved 3 in any direction. It could be anywhere. It could be anywhere that's 3 meters away from this origin. So moved 3 meters doesn't actually help. What about if I say it's moved plus 3 meters, right? Well, that still doesn't actually help. Plus 3 meters doesn't mean anything, because no matter which way you move from here, you've still moved 3 meters. And the plus doesn't give us enough information to know the direction. So it could still actually be anywhere along that 3 meter circle, right? It could still be anywhere. But if I tell you that I've moved 3 meters in the x direction, I'll get rid of the x, so plus 3x, now you know that I'm exactly here, right? That's plus 3x. If I tell you that I've moved plus 3y, then I'm exactly here. Alternatively, I could say I've moved plus 3 meters at an angle of 45 degrees to the x-axis. And that would be exactly along 45 degrees. I would be exactly here, 3 meters at 45 degrees. So you now need a bit of extra information. So in the one-dimensional, the plus or the minus is enough to know. In two-dimensional, plus and minus don't really mean anything, right? They do if you're talking about components. If you're talking about plus 3x or plus 3y, or minus 3x or minus 3y, those mean something. But if you just say I've moved plus 3 meters, that itself doesn't mean anything. And the other thing I want to point out is that as soon as you move to an angular description, so if I'm saying I've moved 3 meters in 45 degree angle, or if I've moved 3 meters at struggling to think of one, let's say 120 degrees to the x-axis. 120 degrees, that's 90, and then plus another 30 is somewhere around here. All right, so that's about 120 degrees. That's still positive 3, because you've still moved 3 meters away from the origin in that direction. You would never say negative 3 meters at 120 degrees, because that doesn't make any sense. As soon as you move to an angular system, it's always positive. So hopefully that's enough information about vectors for now. As I said, I'll try and reiterate some of that as we go through the course, especially when we deal with force problems and two-dimensional collisions and things like that. That's where vectors really start to get a little bit confusing if you haven't grasped them fully. The last part of this is graphs and graph analysis. Hopefully, as I said, you're familiar with graphs. In the maths, the pre-maths quiz, there is some stuff on graphs. So I won't go into too much detail, but you do need to be familiar with them. When we have a frame of reference, we often end up using those same coordinates for the graph. So if we've got somebody that's moving along an x-axis and it's one-dimensional, then usually what we'd end up doing is we'd graph that x versus time, for example, and that just tells you where they were on that x position versus the time of watching them. Sometimes though we'll have two-dimension, x and y, and you might either use the x and the y and graph them against each other, or what's very common as well is to do two graphs, one of the y position versus time and one of the x position versus time. So but usually what happens is that those coordinates that you choose for your frame of reference are the same ones that you're going to end up graphing. I'm just going to do an example now, just to hopefully demonstrate how you would deal with a lot of the sort of the experimental data that we'll get through our course. Here's some position of a person. It's just an x position, so it's one-dimensional motion, but we've been given the time from 0 up to 6. So 0, they start at 0, so that's our origin in the x position. Is also the origin for our time. And we can see that over 6 seconds, they move up to a total of 4 meters. To graph it, you should know how to do this. You just plot the two coordinate systems, your time across the horizontal, your x vertically, and then you just mark on all the different data points. So there's our data points. You then fit a straight line, and that will look something like this. Usually when we're graphing something, we're trying to make it have a linear relationship, which means a straight line fit. We'll normally do it using a computer, which can tell us the slope and the intercept and everything. Here, I haven't done that. I've just done it manually, and you feel free to copy along and draw one yourself if you want. Use that data and just try and get the same result. Again, there is a question on the problem sheet that asks you to do that, to use this, not this data, but similar data, and just draw your own graph and fit a straight line. Once you have that linear relationship, it's good to know what the equation is for that relationship, so how x relates to time. Hopefully you're all familiar with the concept of a straight line equation, y equals mx plus c. Y and x are our vertical and horizontal axes. So in this case, y in that straight line equation is actually x in our graph. X is vertical, time is horizontal. So here we've got x is equal to mt plus c in the system of our graph. M is the slope and c is the y-intercept, which y-intercept means y in that conventional Cartesian coordinates. On our graph, the vertical is x, so it's the x-intercept, just to be confusing. For our equation, the slope is 2/3, so you can just read that off the graph, rise over run. It goes up 4 over 6 across, so rise of 4 over 6 is 2 over 3, 2/3, or 0.667. So our slope is 0.667 and the intercept is 0 meters because it goes through the y-axis at 0. And that means that our equation becomes x equals 2/3 t plus 0. Again, I know I'm repeating this a lot, but hopefully just to clarify it, y equals mx plus c. The y simply means vertical and the x simply means horizontal. And it can get confusing when you have a system like this where your vertical is actually called x, because now the x goes where the y was in our straight line equation, and the x in our straight line equation becomes a t because that's our horizontal. So if it helps, think of it as vertical equals m horizontal plus c, if that helps. There's a couple of terms that we want to define now. Interpolation simply means figuring out what the value would have been between a couple of the measurements. No actual recording happened at this point, but you want to figure out what it would have been if it had been recorded. So you can interpolate. Interpolate, in this case, let's interpolate to see where the person was at 1.5 seconds. And you just draw a line up from 1.5, and then you see that that is at 1. So the x position at 1.5 seconds would have been 1 meter. Of course, we didn't actually measure it, so we don't know that because we didn't get a piece of data for it. But by interpolation, we can figure it out. Interpolation is usually fairly reliable, provided the system, whatever it was, is fairly consistent. In this case, we can see that the person is moving not perfectly steadily. So if I go back to where these dots are, you can see that this one's a bit below, this one's a bit above, a bit below, a bit above, and so on. So the person isn't perfectly adhering to that straight line equation as they move. But it is pretty close, which means interpolation is going to be a fairly good indicator. It won't be exact. It'll have some uncertainty. If you remember uncertainties, there is uncertainty in this scenario, but it will be fairly close to that value. The other thing we can do is called extrapolation, and that means extending the information beyond what was recorded at all. So in this case, the data went from time 0 seconds up to time 6 seconds. We could predict where the person is going to be, say, at 9 seconds. And to do that, we would just look at our equation, and our equation said 2/3 of x plus 0. Right? So 2/3 of x, 2/3 of time in this case. Right? X is equal to 2/3 t. So we have 2/3 of 9, which is 6 meters. So we could extrapolate and say that the person would be at 6 meters after 9 seconds. But it's extrapolation because it's outside, it's extra, it's outside our actual data set. Unfortunately, extrapolation is not always reliable. What you have to do when you are looking at extrapolation is think about the system. Think about what's being measured, think about how it's being measured, why it's being measured, and more importantly, think about whether it's reasonable to assume that motion continues after the time period, or indeed, if you're going the other way, if it started before the time period that was being recorded. So in this case, we have no information about what happened after 6 seconds. They told us the person walked from 0 to 6 seconds and they got this data. They didn't tell us what happened after 6 seconds. Maybe the person sped up, maybe they slowed down, maybe they stood on a landmine and exploded, maybe they lay down and had a nap. We don't know what happened, right? We have no information at all. So what we are doing when we extrapolate is we are assuming that the described motion continues unchanged. So we don't often actually say it, but what we are doing when we extrapolate is we are saying, if this person continued moving in the exact same manner, they would be at 6 meters after 9 seconds. But we normally skip that whole big sentence out the front and we just say they'd be at 6 meters after 9 seconds. That would be our answer. But it's important to remember that you are making that big assumption. And it is a big assumption because we have no information about it. So we have to make that assumption. We don't always state it, but it's very important that you are aware of it and that you state it to yourself, even if you don't write it down in the answer. Right? Indeed, when you're learning these during the first few lessons and things, I expect you to actually write these assumptions down. Right? Don't just assume them in your head and then leave them. Write them down or ask about them. Right? Confirm them. So that's the course content for this lesson, and indeed the end of the first section. That is lesson 3. You now have hopefully all the information you need to start on the actual physics next week. I say actual physics, we did sort of start it talking about systems and scenarios and frames of reference. That is physics more so than maths, because it's talking about how we take those numbers and apply them to real world stuff, which is physics. But really it is just a tool that you need to be very familiar with and very comfortable with, and it is mostly math based. So do go and check out all the problem sheets. There is one for each lesson, except for 0, because that was sort of a pre-lesson. Lesson 1 only had a couple of questions. 2 and 3 have plenty of questions. Do practice them all. And as I've said on the stream site, do try the problems first. Don't just open the solutions and go, yeah, I could do that, because it's very easy to convince yourself you could, but unless you actually try it, there's no way to be confident that you really could have.